Hello everyone and welcome back to our Calculus 1 course. Today we are talking about techniques to solving limits. So let's go ahead and review what we were talking about last time, which was going over a bunch of practice problems on the properties of limits. So for our properties of limits, we had the constant value c rule, which said that if we have a limit as x approaches a of c, then that limit is equal to c. For constant multiplication, if we have a function multiplied by a constant value c, then we can take that constant and move it outside of the limit, and we will get that our limit is equal to c times the limit as x approaches a of f of x. For our addition and subtraction rule, if we were finding the limit of two functions that were added or subtracted to each other, then we can say that our limit is equal to the limit of f of x plus or minus the limit of g of x. Same thing for the product rule, is if we have two functions f and g multiplied by each other and we're finding the limit, then we can find the limit of each function individually and then multiply them together. And the same thing again for the quotient rule. If we have two functions f and g in a quotient, so f divided by g, and we're finding the limit, then we can find the limit of f of x and divide that by the limit of g of x. For our exponent rule, if we have a function raised to the power of n, and we're finding the limit of this function, then we can take that n and put it outside of the limit and find the function limit as x approaches a and raise it to the power of n. And finally, the polynomial rule is that if we have the limit as x approaches a of a polynomial, then we can go ahead and plug in our value a that we're looking at into the polynomial, and that will be our limit. So today we are talking about the techniques to solving limits. Here we've got 6 different techniques that we will be using to actually solve limits without having to graph or use the table method. So our first one here is direct substitution. Then we have factoring and elimination, conjugates, complex fractions, trig limits, and finally the squeeze theorem. So our first 4 here, direct substitution, factoring and elimination, conjugates, and complex fractions, these are all algebraic techniques. So these ones we will be using a lot of our algebra that we have learned in previous classes to solve. And in blue here we have trigonometry, so we're going to be using a trig limit. And then finally we have our squeeze theorem, which is a new theorem that we will be talking about and go into detail for. So here we've got just some examples of what these limits might look like, and we will actually work through each of these problems to get a hang of each of these techniques into solving limits. And as we did for the properties of limits, today we are just going to go over these limits, and then we will have another video and we will do many practice problems that involve all of these limits and put them into practice. So our first limit here is direct substitution. This is what we were doing in our last video with our limit properties. So this is taking use of all of the limit property rules and then also making sure that we know our polynomial rule here, as that is one of our most important rules for solving limits. So like I said, limit properties are very important, just as we used last time. We should always be doing the direct substitution first before we go ahead and try any of the other types of limit techniques that we have, just because it might be a problem that you can just plug in the numbers straight away and find the answer without having to do any other algebra or trig techniques to solve the problem. So here we have a graph of this, which is just a parabola that has been moved over a little bit. And using our limit properties from last time, we can go ahead and solve this by just plugging in our a value of 3 here. This is a polynomial, so this rule is really what's applying here. So our a value is 3, so we can go ahead and plug in 3 into this limit. So this is 2 times 3 squared minus 5 times 3 plus 1. And we solve this, we get 2 times 9 minus 15 plus 1, so we get 18 minus 15 plus 1, and this equals 18 minus 15 is 3 plus 1 is 4. So our answer here is 4. Our next technique is factoring and elimination. So our first step for these kinds of problems is to get an indeterminate form from substitution, where indeterminate is something that looks like this, 0 divided by 0. There are other types of indeterminate forms, but we will talk about that in a future video. What we want to do then is we're going to expand the quotient and cancel common terms that we get from that expanded version. And then once we can cancel those common terms out, then we can finally go ahead and plug in our a value with substitution and solve. So for these problems, we actually saw this similar style of problem in our last video, where this is just a hole in a line. But let's go ahead and solve this without using the table method like we did last time to find the limit. So our first step, right, is to get 0 over 0 from substitution, get an indeterminate form. So let's go ahead and just plug 4 straight into our problem first and see what we get. So we plug in 4, this is 4 squared minus 16 over 4 minus 4, and this is equal to 16 minus 16 over 4 minus 4, which does in fact equal 0 over 0. So this 0 over 0 is our indeterminate form, which means that this is not the limit and we have to do something else to get the actual limit. So for this, what we're going to have to do is expand our quotient out. So we have x squared minus 16 in the numerator. Well, this is actually just a square, so we can go ahead and expand this. If we write x squared minus 16 over x minus 4, x squared minus 16 is equal to x plus 4 times x minus 4. So we've expanded that out, and we keep x minus 4 in the denominator. Now we've got common terms with our x minus 4 here, these two, and we can cancel these out because they equal 1. And so now we are left with the limit as x approaches 4 of x plus 4. So now we can go ahead and do our substitution, and we will get 4 plus 4. Which of course is equal to 8. Our next technique is using conjugates. So once again, we're going to get a indeterminate form from our substitution, and once we determine that, then we will have to multiply by the numerator and denominator by the conjugate. So remember, a conjugate is what we have in this table here, is when you have a binomial, and with our square roots here, anytime that we have a binomial, so that is two terms, and one of them includes a square root, then we can use our conjugate, which means that we take the opposite sign of what we have and multiply both the numerator and denominator by that. So here we have a plus the square root of b. The conjugate would be a minus the square root of b. And the same thing for all of these is you've got a minus b, and then your conjugate, you just flip your sign there. So let's go ahead and look at our problem here. Let's go ahead and start by our substitution, how we always want to start. So the limit as x approaches 9, go ahead and plug in 9 into our problem. We get the square root of 9 minus 3 divided by 9 minus 9. This is equal to 3 minus 3 divided by 9 minus 9, which in fact equals 0 over 0. So this is an indeterminate form, and whenever we see an indeterminate form, that means that we have to do something else to try and figure out this limit. I see that we've got a square root in the numerator, and it is being subtracted by 3. So our conjugate is going to be the square root of x, and since we have a minus, our conjugate is going to be plus 3. So let's go ahead and rewrite our problem here. So we've got the limit as x approaches 9 of the square root of x minus 3 divided by x minus 9. So we are going to multiply this by 1 in the way that 1 is multiplying by our conjugate in the numerator and denominator. So this is the square root of x plus 3 on both. So now we can go ahead and multiply. We're going to FOIL our numerator here, and we will end up with x plus 3 square root of x minus 3 root x minus 9. And in the denominator, instead of foiling out the denominator, I'm just going to leave these as they are. So we have x minus 9 and the square root of x plus 3. So now we can simplify the numerator. We get x minus 9, and this is all divided by x minus 9 times the square root of x plus 3. So now we've got common terms. We've got x minus 9 in the numerator and the denominator. So we can cancel these out. Those equal 1. And we are left with finding the limit as x approaches 9 of 1 over the square root of x plus 3. So now we can go ahead and plug in our a value, which is 9, and then take the square root plus 3. So this is equal to 1 over 3 plus 3, which is equal to 1 over 6, 1/6. And we have complex fractions, which is our last algebraic technique. So we are going to once again check to make sure that we do get an indeterminate form, which I don't have written here, but you want to check again for 0 over 0. And we're going to then combine this complex fraction into a single fraction. So we're going to turn our numerator here in this problem from being this complex fraction into a single fraction. So we're going to simplify the complex fraction down. And then finally, once again, we can use substitution. So let's start off by checking once we plug in our numbers. So the limit as x approaches 2 is going to be 1 over 2 minus 1/2, all divided by 2 minus 2. And this does equal 0 over 0. So we have to do something different here, and that is going to be combining our complex fraction. So in the numerator here, the way that we're going to do that is by getting common denominators. So we've got 1 over x minus 1 over 2, all divided by x minus 2. So to get the numerator into one fraction, what we have to do is find the common denominator, which is going to be 2x. So I need to multiply 1 over x by 2 over 2, and 1/2 by x divided by x. So this is going to equal 2 divided by 2x minus x over 2x, and this will all be over x minus 2. So we can go ahead now and actually simplify this. We get 2 minus x over 2x all over x minus 2. And now we've got two denominators here, which means that we can actually combine those denominators together. We get 2 minus x divided by 2x times x minus 2. And 2 minus x is also just a negative 1 times x minus 2. Divide this by our denominator, 2x, x minus 2. So now we have a common term in our numerator and denominator, which is x minus 2. So we can go ahead and cancel these out because they're equal to 1. And we get the limit as x approaches 2 of negative 1 divided by 2x. We can go ahead and use substitution. We do negative 1 divided by 2 times 2, which is equal to negative 1/4. We're now moving on to our trig limits. So these are some fundamental trig identities which you will just have to memorize, which are these two here. The first one is if the limit as x approaches 0, this has to be 0. The limit as x approaches 0 of sine of x over x, then this will equal 1. This x that you see here, sine of x over x, it doesn't have to be x, right? We have x approaches 0, but this could also be the sine of 20x over 20x. They have to be the same in the numerator and denominator, that value, but it does not have to be just x. And then in our second one, we've got the limit as x approaches 0 again of cosine of x minus 1 divided by x. That is equal to 0. And like the first one, this does not have to be x, and this does not have to be x. They just have to be the same. So this could also be cosine of 20x and 20x in the denominator. So let's go ahead and take a look at this problem. We can actually go ahead and do our indeterminate form. We plug in 0, so we get sine of 5 times 0 divided by 0. And this is equal to sine of 0. Sine of 0 is 0, so we get 0 over 0, and that is an indeterminate form. So what we have to do is we have to get this function equal to what we have in the denominator, right? This inside part of the sine has to be the same as our denominator. Right now we have 5x over x. Like we said here, they have to be the same thing. It doesn't have to be x, but they just have to be the same value. So to get that to be the same value, I need this denominator to have a 5 next to it. And the way that we can do that is by multiplying both the numerator and denominator by 5. So we get sine of 5x over x, and we need to multiply by 1, which is 5 over 5. So we can rewrite this now as sine of 5x over 5x times 5. And now we have this fraction here, the sine of 5x divided by 5x. This equals 1. This is the limit. This is our same rule that we were just talking about right here. We've got sine of something divided by the same thing, and we're finding the limit as x approaches 0. So this is equal to 1. So now we have 1 times 5, and so our total limit is equal to 5. And finally today we have our squeeze theorem, the last technique to solving limits for today. And this is arguably the hardest technique that students have to learn. So we will go over it briefly here, and then when we go ahead and do some practice problems in our next video, we'll spend more time focusing on squeeze theorem problems and really digging into them to make sure that we can understand them well. So you might also hear the squeeze theorem called the sandwich theorem or the pinching theorem. They all kind of talk about what this limit looks like, and we'll talk about what it looks like in just a second here, but we will finish going through just the steps of the squeeze theorem first. So for the squeeze theorem, we want to identify the squeezing functions of f of x. And once we determine the squeezing functions of f of x, that will give us 3 functions to deal with: g of x, f of x, and h of x, where f of x is the function that we were given. That's the function of the limit that we were looking for. And then g of x and h of x are our squeezing functions. If g of x is less than f of x, and f of x is less than h of x, and these are also equal to, less than or equal to, and we have that the limit of g of x is equal to the limit of h of x, these both equal L, then our limit of f of x must also equal L. So the easiest way to understand this is by drawing a picture of what's going on. So if we have a graph here, this is just something that you are going to have to get a hang of, and once we do some more practice problems of this, you'll start to realize what these functions are going to look like. Our function here, so we're going to call this f of x. F of x is the x squared sine of 1 over x. And this function looks something a little like this. For this function, right, we start out pretty low, we go up, and since it's sine, we're gonna have that periodic nature to it where it's going up and down. And right here in the middle, at the origin, if you were to use the table method and the left and right-handed limits for this function, you would never reach a value, because this is always oscillating between positive and negative values. So no matter how close you get to 0, you're never going to actually reach a value. So you can't find your left and right-handed limits with the table method. So if you were to do the table method, and I will just write a quick example here. These are made up values because I don't know the actual values, but it would look something like this. If you're looking from the left-handed side, so from the negative side of this graph, and we're looking as x approaches 0, then we want to choose numbers slightly less than 0. So let's choose -1, -0.5, -0.1, and -0.01. If you were to choose some values for this, your f of x would end up looking something like a positive number, then a negative number, then a positive number, then a negative number. And you would continue down this line, always switching between positive and negative, and you would never actually reach a value that you approach. So you can't use your table method for the left and right-handed limits. So what we have to do here is we have to use the squeeze theorem, which is finding two functions that we can actually fit this purple graph in between. And so what I mean by that is we need to use this function to find two other functions inside of it. And the way that we do that is we look at what's being multiplied here. So we've got x squared being multiplied here. This means that we have two different functions where g of x is going to equal the negative value of this thing that we've circled in orange here, so negative x squared, and h of x is going to equal the positive version of this, x squared. So g of x and h of x are our squeezing functions that we were talking about. They're going to be our squeezing functions. They're functions that we know and that we can find the limit for. So let's go ahead and graph our function. So we've got g of x, which is less than f of x. And I know that because x squared looks something like this. Negative x squared, right? It's a parabola. And maybe I draw it a little bit better. You get a parabola that's upside down, and it's getting closer and closer to 0 at the point 0. For h of x, we've got a positive x squared, so that's going to be the positive parabola, getting closer and closer to 0 from the positive end. So from this graph, you can see that we've got our f of x in purple here that gets smaller and smaller towards the origin and expands out. But it's always in between our two functions. It's always less than the red, h of x, and it's always more than blue, our g of x. So we're squeezing our function of f of x in between g and h and x. It's always going to be in between here. So no matter where this is going, up and down in the middle, it's always going to be less than the red one and always going to be more than the blue graph. And we actually are able to find the limit of both of those graphs here. So if we do blue for g of x, the limit as x approaches 0 of g of x, which is negative x squared, well, we just plug in 0 and we get 0. The same thing for h of x, the limit as x approaches 0 of positive x squared. Again, substitution, you plug in 0 and we get 0. So I know that our f of x, which is in purple, is always greater than blue and always less than red. And I know that the limit as x approaches 0 of g of x is 0, and the limit as x approaches 0 of h of x is also 0. So what we have here, right, is what we have written in this section right here. We've got g of x is less than f of x is less than h of x, which is in our graph. And then the limit of g of x is 0, and the limit of h of x is 0. So this L is equal to 0. Since f of x is always greater than g of x and always less than h of x, and both of their limits are 0 right at the origin here, then that means that our limit as x approaches a of f of x must also equal L. So our limit as x approaches 0 of f of x, which is our x squared sine of 1 over x, this must also equal 0. And I have a graph here made in GeoGebra, so it is a little bit easier to tell what's going on here versus my own drawing. Our red line here, that's our h of x value, which was x squared. And in blue, we've got g of x, which is negative x squared. And the purple is squeezed in between them. It's always going to be less than the red and always greater than the blue, which means at our limit of interest at 0, it's going to be less than or equal to the red and greater than or equal to the blue. And since they were both 0, then at the point 0, our limit must also equal 0 for f of x. And as a review, here are our limit techniques. So we've got direct substitution, which is what we did in our last video, which is using limit properties, only limit properties, especially our polynomial rule. And this should always be the first thing that you try, just in case you are able to solve it using direct substitution, you want to be able to do that first before wasting any time doing any of these other techniques, before realizing that you could have just plugged it in. Our next one was factoring and elimination. So that's when you have something of this setup where you can actually expand something in the numerator or denominator and cancel a common term out to remove a hole in the graph. For the conjugates, we use this if we see a square root and we are adding or subtracting some number with it. Then we can actually multiply by the conjugate to remove that square root and solve with substitution. With complex fractions, this is if we have a fraction in a fraction. What we want to do is find a common denominator to simplify and reduce this complex fraction. For our trig limits, this is if you see something of this style with a sine or a cosine, or something that you can actually turn into sine or cosine, and use one of these two rules here, which you have to memorize, which are the fundamental trig identities, which is the limit as x approaches 0 of sine of x divided by x is equal to 1, and the limit as x approaches 0 of cosine x minus 1 divided by x is equal to 0. So remember that these x's don't have to be x, it just needs to be the same in the numerator and denominator. Same for cosine. And finally, we have the squeeze theorem, which is something of this form, where you will see some function multiplied by a sine or a cosine with 1 over x in some form. And for these, you want to find the squeezing functions, g of x and h of x, which are less than or equal to and greater than or equal to f of x, which is what you were given. And then find the limit of both of those, and if they both equal the same thing, then your limit of f of x is equal to that same value. So that's what we've got for our techniques for solving limits today. In our next video, like last time, we are going to go over a bunch of different practice problems that go over all of these so we can really get a good hang of computing limits.